Hi, this is Dr. Xu teaching design of experiment for engineering research. Today we will talk about simple comparative experiments. A lot of times we do experiment to compare two products. The example shown here is adding certain chemical to cement to increase the curing time, which is denoted as the treated material. The untreated original cement is denoted as original material. We know that the treated material has a shorter curing time, which is desired in practice, but we would like to know if the material strength has been changed due to the addition of the chemical. 10 samples were made for both original and treated material for strength testing, and the results are plotted on this dot plot, with red dots represent the strength for the original material and the green dots represent that of the treated material. We also calculated the sample average. So for the original material, the average strength is 17.92, and for the treated material, it's 16.76. Now you may want to make the conclusion that the treated material weakens the strength, but wait, is it possible that the difference between the two tested average are merely due to experimental and random error, and adding the chemical actually does not cause any change to the material strength? How do we know that the tested differences are due to random errors or due to the chemical effect? I will show you how to solve it using hypothesis testing. Basically, this type of experiment is very commonly seen where we compare two products and would like to know if they are different or basically the same. The sample average is represented by Y bar, and we use the Greek letter mu to represent the population mean. So the population mean for the treated material is mu1, and the population mean for the original material is mu2. Since we're now familiar with the hypothesis testing method, it is not hard to form the null hypothesis as mu1 equals to mu2, and the alternative hypothesis as mu1 not equals to mu2. Previously, we know the sample average for one material. So previously, we know Y1, and we know the true population mean for the other material, and we know mu2. And we have done hypothesis testing for that type of problem. But in this example, we only know the sample average for the two material, Y1, Y2, without any information about the population means, mu1 and mu2. How do we solve this problem? Before we solve it, let's write the hypothesis in a different form. This hypothesis, equivalently, we can write the null hypothesis as H0 is mu1 minus mu2 equals to 0. And the alternative hypothesis, HA, is mu1 minus mu2 not equals to 0. These two hypotheses are the same. We know that the sample average Y bar 1 is normally distributed and Y bar 2 is normally distributed as well, and the two sample averages are independent. In this case, Y bar 1 minus Y bar 2 will be also normally distributed. In case of a smaller sample size here, it is a t-distribution that is related to the degree of freedom. For a t-distribution, we would like to know three parameters: the population mean, mu, Y bar 1 minus Y bar 2. The standard deviation, sigma Y bar 1 minus Y bar 2. And the degree of freedom, df. This t-distribution is centered at mu1 minus mu2. The standard deviation equals to square root of the standard deviation of the first product square divided by the sample size of the first product plus standard deviation of the second product square divided by the sample size of the second product. Because we don't know the standard deviation of the population sigma 1 and sigma 2, we can use sample standard deviation as estimate of these two parameters. So equals to square root of S1 squared divided by N1 plus S2 squared divided by N2. This expression can be derived using the probability theory, and we will not go into that detail. If there are good reasons to believe that the population standard deviations are equal, so if sigma 1 equals to sigma 2, sigma 1 is probably equals to sigma 2 because adding the chemical will not add additional experimental error. Then we can obtain an improved estimate of the sample average standard deviation for each product as S pooled square equals to S1 squared by N1 minus 1 plus S2 squared by N2 minus 1 divided by N1 plus N2 minus 1. So if sigma 1 equals to sigma 2, we say SP as a good estimate for S1, and the same, we use it as a good estimate for S2. We can substitute this value to here and here, then this equals to SP square root of 1 divided by N1 plus 1 divided by N2. Sorry, here should be minus 2. And in this problem, the degree of freedom equals to N1 plus N2 minus 2. Here shows a summary of the parameters for the t-distribution for y bar 1 minus y bar 2. So the curve center is mu1 minus mu2. The standard deviation can be calculated using this equation if we believe sigma 1 equals to sigma 2, and this SP is calculated using S1 and S2. The degree of freedom is N1 plus N2 minus 2. Now the problem became the same hypothesis problem we saw before. We compare the difference of the mean to a known value of 0. And we know the sample average difference distribution, so the distribution of these is a t-distribution. We assume the null hypothesis is true and calculate the p-value of the sample average y bar 1 minus y bar 2 using significance level of 0.05. If the calculated p-value is less or equal to 0.05, we reject the null hypothesis, otherwise we accept the null hypothesis. To find the p-value, we will need to calculate the t-value. Generally, t equals to the value we are calculating the t-value for minus the population mean divided by population standard deviation. Here, y is y bar 1 minus y bar 2, and mu is 0 because we assume that the distribution of y bar 1 minus y bar 2 is a t-distribution with population mean of 0. The sample average difference population standard deviation can be estimated by using this equation, and the SP is calculated using S1 and S2. So putting things together, if sigma 1 and sigma 2 are equal for the two products, we can calculate the t-value using this equation. In this equation, SP can be calculated using this equation. And the degree of freedom is the total number of sample size minus 2. We have been using this part of the data previously, so we know y bar 2 and S2. The sample average for this data is provided here, so we only need to calculate S1. This is the equation to calculate S, so S1 equals to square root of
17.5 minus 17.92 square plus 17.63 minus 17.92 square plus 18.25 minus 17.92 square. We will do this for each of the numbers here. So this one, this one, this one, all the way to the last number. So the last one is 18.15 minus 17.92 square divided by n minus 1, so 10 minus 1.
Or we can use Excel, the stdev.s function. The stdev.s function is the function to calculate sample standard deviation, and the stdev.p function is the function to calculate population standard deviation. We copy this data to Excel, and we use the function equals to stdev.s parentheses In these parentheses, we select all these numbers, enter. So S1 equals to 0.248. Now we have got all the numbers required to calculate the t value. So we firstly calculate SP. This equals to 0.248 squared by 10 minus 1 plus 0.316 squared by 10 minus 1 divided by 10 plus 10 minus 2. The result is 0.081. And then we calculate this part equals to 0.081 by 1 divided by 10 plus 1 divided by 10 equals to 0.127. Therefore, t equals to 17.92 minus 16.76 divided by 0.127 equals to 9.132. One thing worth mentioning is, as you can see, the two standard deviations S1 and S2 are not too much of a difference. Thus, we can assume that the two population standard deviations sigma 1 and sigma 2 are equal. In this case, we use this equation to estimate the standard deviation. Now with this t-value, we can find the p-value using Excel as well. So p-value can be calculated using, we use the function equals to t dist parentheses. The first parameter is the calculated t-value. That's 9.132. The second parameter is the degree of freedom. It's 10 plus 10 minus 2. That's 18. And the last parameter is tails, because we only care about they are equal or not. It's a two-sided problem, so two-tailed distribution. Enter. It's a very small value, 3.5 by 10 to the negative 8th. Now we can draw the conclusion, because p equals to 3.5 by 10 to the negative 8th, which is much smaller than 0.05, we reject the null hypothesis and conclude that the data provide convincing evidence that there is a difference in average strength of the two tested material. Specific to this problem, if the average strength is different, we can also conclude that the tested material strength is less than the original one. This means although the added chemical resulted in a preferred shorter curing time, but it reduces the material strength, which may be a downside. The next natural question is that how much stronger the original material is than the treated material. From the above hypothesis testing, we know that mu y bar 1 minus y bar 2 does not equal to 0. Using previous knowledge, we can calculate the confidence interval of this mu value. If we want to find the 95% confidence interval of this mu value, we will need to find the critical t values T1 and T2, with the area of these being 0.025 and here 0.025. The general equation for calculating the confidence interval for a t distribution is this. Here we don't know the mu, but we use the sample average y bar 1 minus y bar 2 as a good estimate. Also, we don't know the standard deviation of this distribution, but we can use the sample standard deviation we have introduced before as a good estimate for sigma. From the t distribution table, the one-sided area is 0.025 and the degree of freedom is 18. So the t value on the right is positive 2.101. So here T2 equals to positive 2.101, and on the left T1 equals to negative 2.101. So the area here is 0.025 and the area here is 0.025. And the confidence interval can be calculated using this equation. In our example, this is 1.16 and this is 0.127. So the calculated 95% confidence interval is 1.16 plus minus 2.101 by 0.127. And the result is 0.89 and 1.43. So in addition to the previous conclusion, we now can conclude that we are 95% confident that on average the original material is 0.89 to 1.43 stronger than the treated material. To sum up for the procedures conducting hypothesis testing for difference of two means, in the situation of sigma 1 and sigma 2 are equal. How do we know sigma 1 and sigma 2 are equal? Most of the time we can calculate and compare sample standard deviation S1 and S2. If they don't differ too much, we can believe that sigma 1 and sigma 2 are equal. We will form the null hypothesis as mu1 minus mu2 equal to 0 and the alternative hypothesis as mu1 minus mu2 not equal to 0. Using a significance level of 0.05, we will calculate the sample average for each product and calculate the standard deviation for each product. Then, because sigma 1 and sigma 2 are equal, we use the pooled standard deviation and use this equation to calculate the t-value. With the t-value and the degree of freedom, also we know we are doing a two-sided hypothesis testing, we can find the p-value. If the p-value is larger than 0.05, we accept the null hypothesis. Otherwise, we reject the null hypothesis. If we reject the null hypothesis, we can also further calculate the confidence interval of mu1 minus mu2, and the equation is shown here. Alright, this is Dr. Xu. Thank you very much for watching. I will see you in the next video.